All right, welcome back to Easy Math with Nick. Today we're on video number 14, and we are going to be doing an AP Calculus free response question from this year's exam. And the topic of this free response question is volumes of solids. Okay, this was number 2 for the calculator section. But I'm going to be treating this question as if it was a non-calculator. What I mean by that is I'll only be setting up the integral and not plugging in my calculator. We'll see what I mean by that very shortly. So the question asks, the shaded region R is bounded by the graphs of the functions f and g, where f of x equals x squared minus 2x and g of x equals x plus sine pi of x, as shown in the figure. Okay, pretty cool. They give you the figure. That's nice. Calculus should be in radian mode. Please put in radians if you didn't. That's a bad mistake to make. All right, so they asked find the area of R. That's part A. So we're doing part A now. I'll do it in green. All right, so actually, no, I'll just say I'm doing part A. Okay, so the area of R, when we're looking at our graph here, it roughly looks like this, right? I'm going to do very crude drawing of it. Something like that, right? The region R is represented by, if we're trying to find the area of that region R, we're going to have, if we look at just a slice of that region, like a one-dimensional, well, it's not really one-dimensional, that's one point. If we look at a slice of that region, it's going to be g of x minus f of x. If we want to find the entire area of this, we're going to have to integrate, as we're going to add up all these little slices with length g of x minus f of x, right? That makes sense when we look at the graph. As say, let's look at the point, let's see here. They don't have any nice points that I can use to illustrate this, but hopefully you see that if you can think about this as a tiny rectangle almost, right? We're going to be integrating to add up all these tiny rectangles so we can find the total area of that region, right? And these rectangles, of course, have a width of dx and a length of g of x minus f of x, because g of x is our top function here. F of x is what we have on the bottom, so that's why we're subtracting it. We're not adding, because if we were adding g of x and f of x, we wouldn't be dealing with region R anymore. We would have we'd be dealing with lengths that go above g of x. So that's not what we're doing here. We're not adding, we're subtracting. And this makes sense too for values under the x-axis. You might think we still subtract. Yes, we do, because we're dealing with area. We're dealing with length is going to be a positive value, right? So if we're looking at g of x minus f of x and f of x is a negative value, that doesn't really change anything, right? We're still finding the length of what that is. So if we're at, let's say, I wish there were nice points to use here so I can illustrate that, right? But I think you can see where I'm getting at here. We're trying to, if we were adding, let's say we had the point 1, 1 and 1, -1, we would find the length of that to be 0 if we weren't subtracting, right? But the length of that's really 2. So you can see where I'm getting at here. That's not an actual point on there, but I like using points to illustrate what I'm trying to say here. So we're going to be, so if we have one, the area of one of these little rectangles is going to be g of x minus f of x. That is our width. That's our length, right? Times dx. But we want to find the entire area of that region, so we're going to be adding up all the rectangles from all these little infinitesimal rectangles from 0 to 3, as that's the region R that we are given. So the answer for this question is going to be evaluation of 0 to 3 of g of x minus f of x dx. And so I'm going to put this in a form where I'm substituting in g of x and f of x. So I'll put in a form that's ready to put in your calculator if you want to do this yourself. So we'll have x plus sine pi of x minus x squared. Don't forget to distribute the negative, so it's going to be a plus 2x dx. And you can simplify that as you want. So that would be what? Minus x squared plus 3x plus sine pi of x. So I'll write that. Yeah, I'll put that plus 3x dx. So that was our answer for A, and I will circle that in green. All right, so that wasn't so bad, right? You had to realize that our limits here are going to be from 0 to 3, as that is the starting point and ending point of the region we're given. So that was something you had to take note of. And as well, you had to be familiar with the notion of that we're adding these infinitely many small rectangles of width dx. And our length is going to be g of x minus f of x, because g of x is our top function there, f of x is our bottom function. So that is what we have there. You could also break up the integral. You could have integral from 0 to 3 of g of x dx. So you could say, instead, this is equivalent to saying, if you think this is more, if this makes more sense to you, because of a property of integrals, this is equivalent to what we had. So we can have the area, we could have the area under g of x here minus the area of f of x here, and we would get the same value that we got there. And remember, we're still going to end up with a positive value, because we're going to have, even if the area of g of x was smaller than that of f of x under the x-axis, we will still end up with a positive value, because we have the positive area under g of x, and then we have the negative area bounded by the x-axis and f of x. So, and we're subtracting that, so positive minus a negative still yields us a positive no matter what. So there you go. Hope you can kind of see where I was getting at there. So let's start the next part now. That's just another way to think about it, if that's easier for you. Okay, part B, region R of the base of a solid. Okay, so now that region's the base of a three-dimensional solid. Okay, for the solid, at each x, the cross-section perpendicular to the x-axis is a rectangle with height x and base in region R. So if we, I'm not going to draw a diagram because my drawing skills are horrible, but I will draw a rectangle here, representative rectangle. If we want, they tell you that this rectangle is perpendicular to the x-axis, and it has a height x and base in region R. So its height is x, and the base is in region R. So region R is the base of a solid, so therefore this base must be g of x minus f of x, right? Because that is, if we look at our graph here, the rectangle is sort of going to be like these little, almost similar to these representative rectangles we drew here. But the key difference is that our dx was parallel to the x-axis, right? It's on the x-axis. But now we're dealing with something that isn't parallel to the x-axis, and it is instead perpendicular to the x-axis. So it's not going to be on the x-axis. It's sort of going to be perpendicular, if that sort of makes sense. It's sort of hard to think about there, but if I can draw nicely in 3 dimensions, we can sort of see that. I'll try. I know that looks like a cross. That's not what I'm getting at. But if we're looking at 3 dimensions here, and we have this under x-axis, and they sort of meet there. I know that's a really bad image, but the our solid here is going to be formed by these rectangles that we're drawing. And so this rectangle has a height x, and its length is going to be this coordinate minus this. And what was this? This was g of x, and this was f of x. So that's where we got what we got here. Imagine that x is, this x here, the height of the rectangle, is sort of coming out to you on the page. It's sort of popping out. I tried to show that, not very well, but that is what we're getting at. And so in order to find the area of this 3-dimensional solid, we're going to have to add up all these little slivers. These slivers are sort of, you could sort of think of them as rectangular prisms too, because they're going to have a width of dx. And so for these types of questions, we're going to set up our integral as from a to b of a of x, the area of our representative shape dx. And this should make sense, right? Because we have, if I draw a quick rectangular prism here, our length is g of x minus f of x, right? Our height is x, and our width is dx. So the dx is parallel to the x-axis. It's on the x-axis. Our length is also on the x-axis, but the height pops out of the page, right? It comes out of the page, and they told us that the height is x. They gave that to us. We don't have to infer that. That's something they tell you. The height is x. That won't always be the case. They can easily tell us the height is x squared if they want to be fancy. But that's just something they define. So what are our limits now? Well, it's still going to be 0 to 3 because that is the region R. The region R is the base of a solid, and that goes from 0 to 3. So when we set up our integral, it's going to be from 0 to 3. In the area of the solid, we just indicate that as a of x. You can sort of think of it like a function if that helps you. It's going to be the area of this representative rectangle we drew up here. So it's going to be g of x minus f of x brackets times x, and then we have a dx. Okay, so that's essentially going to be what we have within the integral is one of these rectangles that we're going to be adding up infinitely many of. Sort of the same idea we saw with the last question, but now we have an extra dimension, and that extra dimension is that height x that's popping out of the page, and that's what I tried to do there. But now if we plug in what we had before, if we g of x minus f of x, we did that in the last question, so we don't have to redo the work there. G of x minus f of x was minus x squared plus sine pi x plus 3x dx, right? Plus 3x time x dx. I'm just getting this into a form where you can just easily plug it in your calculator to solve. So minus x cubed plus x sine pi of x plus 3x squared dx. So this is your answer for part B. That should be correct. Okay. Plug that in your calculator and get an answer. Make sure you're in radians, right? Okay, now for part C, I'm going to use a different color. I'll use, how do I change color? Sorry, here, give me a moment. I'll go to orange now. Actually, no, I'll use purple. I like purple. Done. Purple's my color now. Okay, on to C, number C. Right, but do not evaluate integral expression for the volume of solid generated when the region R is rotated about the horizontal line y equals -2. Okay, so let me draw this image again of the graph so I can show you. This is sort of a hard question to mentally understand, so drawing a graph here is almost necessary. So we have what? This weird region that sort of looks something like this, right? This region R. So we call this R. So now we're at -2 and we're rotating it around this line. So when we rotate it, we're going to have a reflection centered at that line, a reflection across that line, sort of like a mirror image on the opposite side of that line. So it's sort of going to look like this, right? Horrible drawing, but you can kind of see this is still our region R. Now we're rotating it about that line. So our y-axis or x-axis. So you can kind of see what I'm getting at here. If we want to write it, we're still not evaluating. It tells us not to here, actually. Integral expression for the volume of solid generated when we rotate that region, we're going to have a gap from here to here, right? This region has no area in it. So we're going to sort of have almost like a weird donut type shape here when we rotate that region around the line, y equals -2. So when we look at just a slice of this donut, this is called a washer. You might have remembered that from your calculus class. The outside part of this washer is going to be that region R. Okay, no, it's sort of Yes, it is sort of hard to grasp here, but yes, the outside part of that region is R. So that is how do I want to express this? Yes. Okay. The outside part of that is going to be yes, that's right. It's going to be g of x minus f of x. I was thinking if I should write out the whole function, but I don't think I'll do that because it's just for illustration's sake. And then on the inside, we're going to have, if we look at our graph, if we look at the question, again, rotate about the horizontal line y equals 2. The inside has a radius of r equals -2, right? But radius can't equal -2, so the inside is going to be, yes, it's going to be -2. Yes. Do I want to have -2 or +2? Give me a second. Yeah, so when you take a look at our graph here, when with the graph you're given, it's much more obvious here. When we look at what's going to be the empty part of our representative washer or representative donut, like two-dimensional donut, our radius here, the empty radius, is going to be f of x. Is going to be that f of x value -2. Right, okay. So, I'm sorry, f of x plus 2. My bad. So if we have, let's say we're at 1 comma, well, okay, I wish it came out nicely, but it's going to be, no, it does. It's going to be 1, yeah, it's going to be 1 comma -1. So our f of x is going to be -1 plus 2 is 1. So the radius there is 1. That makes sense here. So instead, if we're at, let's say, 2 comma 0, our f of x is 0 minus 2, our radius is 2 there. So that's going to be the radius of that empty part of our empty part of our hole. So now if we look at what we have down here, let's reevaluate what we have here. So the empty part of our hole is going to be f of x plus 2, and the outside of our the solid we're generating here is g of x, right? That's our outside function. That's what we're rotating around the x-axis. That's the best way to think about this here, because that's going to be what we're rotating around the x-axis, and then we're taking out that middle part. You can also think of, there's another way to think about this as well, but I think this is the easiest to comprehend. So we're rotating the g of x around the horizontal line, y equals -2, not the x-axis, I might have misspoke. We're rotating g of x around the horizontal line, y equals -2. And when we do that, we have a solid with no holes in it. But then we have to take a hole out, because a hole that has a radius of f of x plus 2. And so the outside is going to be g of x. When we take a look, this is our representative washer. I think that's the technical term that you use in calculus class. It's called the washer method. So that's our representative washer. So if we take a look at the area of one of these washers, it's going to be this washer is it's not really it's not really two-dimensional. We have a three-dimensional washer here. So imagine this has I drew that very horribly, I'm sorry. Imagine this has a width of the x, because we are revolving around the horizontal line. So we're going to be working in terms of x here when we look at that width. So what is the volume of a cylinder? Pi r squared h, right? And we're dealing with a cylinder minus a smaller cylinder, so we could have the hole in the middle, right? So we're going to have pi g of x squared, and our height, it's really height, right? It's not width. When you're looking at the graph, it's sort of width, but it's really height. pi g of x squared dx is going to be on the outside. On the inside, we're going to have pi times f of x plus 2 squared dx. And so this is one of our little donuts, right? Our three-dimensional washer. So if we want to find the total volume of that solid generated by infinitely many of these washers, we're going to have to integrate. So I'll use another bracket here, and we're going to integrate. So what are our limits? 0 to 3, again, because that is what the solid is going to extend to, from 0 to 3, because we're still dealing with that region R. And so for the sake of time, I'll circle this as our answer. Let me erase this. Actually, I'll move this. All right, for part C, if you plug in g of x and f of x, you'll get to the point where you can solve. But if you want to think about this another way, I think the way I mentioned it is the most logical, because we have our g of x on the outside. That's going to give us the outside of our ring, of our wash, of our donut, whatever you want to call it. And then f of x plus 2 is going to be the gap on the inside. It's not f of x minus 2, because if it was f of x minus 2, that doesn't really work, right? That would give us a hole that's bigger than what it actually is. It would give us a negative value. That doesn't really make sense. Yeah, that's not right. So if we had, like I showed the example here, I'm just going to repeat myself because I think I went a little quick with this. If we're at the point 1 comma negative 1, the radius of the distance we are from the horizontal line negative 2 is going to be negative 1, right? Because we have f of x plus 2. What's f of x? Negative 1 plus 1 is 1. So that distance is 1, I should say. The distance is 1, not negative. So now if we're looking at the point 2 comma 0, we'll have f of x is 0, and the distance from the horizontal line y equals negative 2 is going to be what? 2. Our distance is 2 because it's f of x plus 2. What's f of x? 0. And if we really want to extend this to the point 3 comma 3, the distance from 3 to the horizontal, the distance from that point to the horizontal line y equals negative 2 is 5. And that's f of x plus 2, right? What's f of x? 3 plus 2, 5. So that's what I was showing here with these little horizontal lines I drew. Okay, enough with that question. I'm going to go back to red. I should use a different color. I'm going to use a different color now. I'm going to use a nice blue for this last question here. Why didn't save it? Done. I have to click done. Unfortunate. Okay. Okay, so D says it can be shown that g prime of x equals 1 plus pi cosine pi of x. Find the value of x for 0 to x, between 0 and 1, non-inclusive, at which the line tangent to the graph of f is parallel to the line tangent to the graph of g. So when we say that tangent lines are parallel, that means the derivatives are equal. So what point is the derivative of f equal to the derivative of g, right? Because the derivative is the slope of the tangent line, right? And when two lines are parallel, their slopes are the same. So essentially, they're asking in a fancy way, when is the derivative of g equal to the derivative of x? So they gave you g prime of x, but in order to find when the derivatives are equal, we need f prime of x, right? So f of x equals x squared plus 2x or minus 2x? I think it was plus 2x. No, it's minus 2x. Whoop, womp, womp. Short-term memory. And if we want to find f prime of x, that's easy, right? 2x minus 2. If we messed that up, too bad. Sorry for you. But there you go. Wasn't that easy? We're not done yet. We have to set that equal to g prime of x, which they were nice enough to give you, even though you should be expected to find out on your own if you had to. G prime of x is 1 plus pi. Oops. I got to draw an equal sign. 1 plus pi cosine pi of x. Right. Let me check if that's right. 99% sure that's right. Yes, that's what they gave you. Okay, so now we set that equal to f prime of x to find value for x at which these will be equal. I'll try to see if I could do this. Setting these two equal. Okay, now subtract both sides by 1, so we'll have 2x minus 3 equals pi cosine pi of x. And this is the point where you probably, not probably, definitely want to use a calculator here, but yeah, because the pi out front here makes this way too difficult to solve otherwise. So yeah, this is where you would just plug both of these equations into your calculator, see where they intersect. I'll go grab a calculator and find an answer here. I'll be right back. Oh, look, how funny is that? I have these equations in my calculator from when I took the exam. I guess I haven't used a specific calculator since the calculus exam. That's funny, right? So I already have this graphed. They asked for the intersection point between 0 and 1. They're looking at the graph. There are 3 intersection points, but only one of them is going to be between 0 and 1. So if we're looking for intersection point, you would do second and click the trace button so you could get to, the calculations tab and go down until option 5 where you see intersect. It'll ask first curve. On the first curve here is going to be the cosine function, that weird cosine thing that we have there. And so you pick that, and then when you're looking at the second curve, make sure that we're sticking close to the first intersection point. And now we're dealing with the linear function that we have there on the left. So once we pick both curves, it's going to do a very good estimate of the intersection point, and we get 0.6758 as equals x. I think you went to 3 decimal points on the exam, but that is what we got as our answer. That's the only time I really had to use a calculator, because up here I just wrote the integral to save time. I think I made everything pretty clear. For this question here, it's sort of, we're going from more basic to more complicated examples as we progress through this question. We started off with just a representative rectangle when we're trying to find the area of R. It's really the area bounded by g of x in the x-axis subtracted by the area bounded by f of x in the x-axis. That's really what we're doing here. And that's how we get our answer. Yep. And so we do, if we're looking at if we're doing that representative rectangle for part A, the length of it, or you could think of it as the height, is going to be g of x minus f of x, because g of x is the top function, f of x is the bottom function. That makes sense, right? And our infinitesimal width is d of x. And so we're going to be adding up infinitely many of those little rectangles, so that's why we have the limits from 0 to 3. That made sense, but in part B now, we're adding another direction. We're now dealing with a 3-dimensional solid, and now it has height x, and the base is in region R. So the base, the length of the base is going to be g of x minus f of x, and the width is going to be dx, because we're dealing, if we're looking at a representative rectangular prism now, because we're dealing with 3 dimensions. As I drew here, our width is going to be d of x, and our length is going to be g of x minus f of x. But now we're dealing with a 3rd dimension that pops out at us at the page, and they give that to you. That is going to be our height x. So now we're adding up infinitely many of these rectangles that have infinitesimal width. So now we're dealing with another dimension. So that reflects in our integral as we add another factor in there. Now we have an x in there to represent our height. So we just took it a step further. So we're taking part A a step further there. For part C, it sort of just flips the stage on us now. Now we were dealing with another 3-dimensional solid, but now we're dealing, now we have a gap in the middle as we're rotating the region R around the horizontal line y equals -2. And that creates a gap. And that gap is going to be represented by f of x plus 2 for the reasons I showed twice before. And our outside function, the outside of our solid, is represented by g of x, rotated around that horizontal line. So if we just rotated g of x around that horizontal line, we would have a solid with no gaps, right? But we have that gap, and we need to represent that gap by f of x plus 2. It's not just f of x, because we're not we have to account for that the fact that the horizontal line's at -2, and not, I guess that's the I guess you wouldn't be don't overthink it. You need the +2 there for reasons I showed before, and so essentially to find the volume of that solid we're generating, it's going to be the volume of the solid generated if we just rotated g of x around the x-axis, and we're going to subtract. We're going to find that volume and then subtract the volume if we are rotating f of x plus 2 around the x-axis. And that's going to get us the volume of our solid. So that's represented by the integral we did there. Because the volume of a cylinder is pi r squared h. Okay, we're in geometry class, right? And the last question, just part D, is usually just a curveball question to trip you up after you did all your wonderful work in the prior parts. And that pattern shows in this question, as it asks, find the value of x between 0 and 1 non-inclusive, at which the line tangent to the graph of f is parallel to that of the line tangent to the graph of g. So to restate, they're asking for when the tangent lines are parallel, and that when two lines are parallel, they have the same slope. And what's the slope of the tangent line? The derivative. So you set the two derivatives equal to each other. They were nice enough to give you g of x. G prime of x. So all you had to find was f prime of x, which is rudimentary. And you set those two equal to each other. And unfortunately, well, this is a calculator question, so you're expected to use a calculator. I was just writing the integral in a form where you could just put in your calculator for A and B. And for part C, I gave up. But yeah, if you use a calculator, it gives 0.6758 as the x value at which the line tangent the curve of both f and g are going to be parallel, have the same slope. So that was just a restatement of all the work we did so far. I was going a little quick at some point, so that's why I felt the need to elaborate more toward the end there. But I think this question, God bless you. Someone sneezed in the background. But I think this question was very doable within the time limit. If I wasn't explaining everything so in depth as I am here, it probably would take me around 15 minutes to solve. Probably half the time if I was just going super speed. But it's always good to show your work. Maybe not as much work as I showed here. I just wish I was better at drawing in 3 dimensions, so the drawing a different part B would be more illustrative. But I think I did a good job here. Very colorful video. And thank you for watching. I was hoping this one would be on the shorter side, but I know my viewers are very enduring. So thank you for watching, and next video will be on, I don't want to do next video, probably back to a physics topic, honestly. But don't hold me to that. Maybe I'll change my mind. We'll see you then. Thank you for watching. Again, I said that 3 times now. And see you in that next video. Bye.